Welcome to the experimental math seminar at Rutgers again. Today's speaker is our alumnus, our very esteemed alumnus, Pat Devlin, joined with his student Paulina Trifonov, who will talk about random chomp. Go ahead. As usual, please unmute yourself unless you have something to say. Thank you.
Thank you for the invitation. This was a joint work with Paulina Trifonova. Out of curiosity, I have a cursor that is supposed to be visible on the screen. Can you see it right now? I'm putting it over the word math. Is that visible?
Yeah.
It's kind of right there. Okay, related. If at any point you have any questions whatsoever, or if you just want to chime in and say something, please do unmute yourself and say something. Oh, wow, it's Professor Rosenstein. Hello. It's really nice to see a bunch of familiar faces that I haven't seen in years. Yeah, so I was at Rutgers in I guess until 2017, and I enjoyed going to the experimental math seminar. Very grateful that it's still going strong with new people, and also the continued folks who still like it. Me too. I also like it, and I've been doing some stuff. So what I want to do today, I want to talk about random chomp and maybe also random nim or other classic combinatorial games. As far as I can tell, and I might be wrong, but my impression of some of the kind of research landscape is that we have folks who like games, these combinatorial games, which definitely includes, I would assume, everybody in this talk, combinatorial games, and we have like recurrences, and we have experimentation, and all that good stuff. And there's that group of folks. They like, it's definitely a part of combinatorics. It's finite, it's discrete, you're counting, for sure. There's also, seems to me, a different group of folks without much overlap in a way that doesn't make sense to me. And I would like to pitch for more people in the overlap. There's other people who like questions about probability. And even if it's just discrete probability, if it's nice and finite, and you don't have to worry about convergence or anything crazy like that, because I feel like that would be sort of countercultural to this seminar for me even to bring it up. But we have probability, and it's great. You can do stuff, but there's not much kind of, as I've seen it, if a lot of people I've talked to, I haven't found a lot of people who really enjoy both. And I'm going to try to use this talk as a pitch for those in the audience who like more, sort of the exploratory finite recursive structures, a pitch why you should also open your minds up and fully explore, not that to say that you aren't already, but to continue to embrace the probabilistic stuff, because there's good stuff on both. So I'm gonna start, I guess, with the games, with the chomp part of the title, maybe out of I would like to somehow poll folks. Oh gosh, there used to be a button. I'm not going to figure it out. I'd like to somehow gauge the room. I would like a show of hands. Anybody who does not know what chomp is or would like a refresher. If there's anybody, there's at least one. We're doing it because it is great. So we're going to start there. Chomp. It's the name of the game. So what is it? It's a two-player game. And the way that it works is they have a big candy bar. And I'm going to draw this little candy bar. Whoops. I think Matthew Russell taught me this game. I feel like he did, one of the people in the audience. And for sure, Dr. Z taught me more about this game. And for sure, I've discussed this game with, I don't know, other people in the call yet. So you start with a chocolate bar. And I'm going to say that you take turns eating the chocolate bar, chomping it. Take turns chomping. And when you chomp a chocolate bar, the way that it works is you pick a square that you're going to chomp. Maybe you're going to chomp that one there. And when you chomp, you end up eating everything that's below and everything to the right. You eat all of that stuff because, your mouth goes to the bottom right. You just chomp all that away. And then all of that disappears. So that's how to chomp. And then And now the board looks different. It doesn't look exactly like a rectangle anymore because a piece has been chomped out of it. We got a little staircase. And a question is, I'm getting such a lag in this this thing. A question is, then what happens next? Will you chomp somewhere else? Maybe the next person chomp, over here or something. They can, and that's a boring spot. Let's chomp somewhere else. Chomp there. They chomp that away. Now that piece is gone. It no longer exists. Take turns chomping. A chomp, you pick a square, you eat it, and you eat everything at that level and below and at that level and to the right. You keep going until the game's over. When does the game end? The game ends when you run out of chocolate. Ends when we run out. Oops, that's the wrong thing. My tablet here is lagging considerably. So if I don't know what it looks like on your end, but for me, I talk, I write, and then I wait. So sorry about that. But it ends when we run out of chocolate. And who's the winner? The game is, I'll say it as a game of etiquette. It's rude to eat the last piece. You're kind of not supposed to eat the last piece of chocolate or cake or whatever. That's rude, say. So it ends when we run out. And the person who ate the last piece is the loser. Who ate the last loses. So you really don't want to eat the last piece. It's in a sense, you can imagine that this the top left square, if you ever eat that piece, you'll eat the entire rest of the bar, regardless of what the situation is. And you're both just trying to avoid eating that. If you want, you could imagine something a little bit more morbid. Maybe that piece is poisonous or something, and you really don't want to eat it. Or the slightly more friendly, you're just trying to be a nice person. But you're trying to avoid that one. You keep chomping, and then that's it. You keep going. Good old game. It's finite, and we can ask lots of game questions like who should win and why. And who should win and why is delightful. There was at least some of you didn't know the game, which it means at least some of you don't know who should win and why. So I get to tell you, and it's fun. Who should win and why? And I'll tell you, this is, well, you'll see. For a rectangular board, which is a usual starting point for Chomp, the first player should win. And if they don't win, it's their fault. Or maybe they were, going easy or something. But the first player should win.
If he does, infinitely smart.
Yeah. I'm going to put should in quotes. And we're going to explore what the word should means because, it's not like, as it turns out, it's not like other games like tic-tac-toe, which should end in a tie. And it's pretty easy to get very good at tic-tac-toe. Chomp is different in a way where I'll tell you who should win, but not what they should do, which is very interesting. So why should the first player win? And this is a really beautiful type of argument called a strategy stealing argument. Instead of telling you what they should do, we can, it's a really indirect way to argue that they should win by saying that if the other person has a good idea, then the first player can steal it. So how's it work? It works like, let's suppose that the first player loses, because that's kind of what we'll have to consider. Suppose the first player should lose. I think I need to say that the chocolate bar has more than one piece in it. We'll get to that if we get to that. So let's pretend, for contradiction, that the first player actually doesn't have a winning strategy. What that would mean is no matter what they do, the second player has a very good response. So second player always has a good response. That's exactly what it means to lose. Always has a winning response. For example, in this case, if the first player, they could decide to do anything they want, and regardless of what they do, they can't be clever enough to trick the second player. The second player will always have a good response no matter what move it is. So maybe, for example, the first player, maybe if they decided to chomp this square, the very, very bottom right square, If they chomp that, which they could choose to do so, then the second player has some good response. And maybe you can start to see where I'm coming with this. The second player would respond, and I don't know where they should respond, but in this theoretical, apparently they do have a good response, so it would go somewhere. Second player would go like here or something. I don't know. They would go somewhere. But then, this is the beautiful part of it. If the second player has a good response, notice the first player could steal that move from the beginning. So what would happen is, but the first player could like preempt, I'll say, and preemptively steal that move. If it's such a good move for the second player, whatever that good response is, if it's such a good move for the second player, the first player can say, well, in that case, I changed my mind. I would like to do that one first instead. And the first player does this instead. And it's pretty. The argument is this long, that if the second player always has a good response, what would their response be if the first player nibbles the tiniest corner? The second player would do that, in which case, whatever it is, the first player would choose to do that initially. And then I guess the second player is in trouble because that's evidently a good move. This is really beautiful strategy stealing argument. The same exact argument says things like tic-tac-toe, the first player shouldn't lose tic-tac-toe because if for some reason they should lose, they waste their first turn and then pretend to be the second player. That's effectively what's going on. In Chomp, there's a way to waste your first turn by nibbling the tiniest bit. It's effectively zugzwanging your opponent, forcing them to have the initiative when apparently that is bad. And if so, you can't be stuck behind the 8-ball or whatever. It's beautiful. A beautiful argument that says apparently the first player should win because this game can't end in a tie. And yeah, the first player can pretend to be the second player. Beautiful. So from a game point of view, in some sense, part of the question is automatically over. We know for Chomp, you're trying to chomp this chocolate bar, chomp it, chomp it, chomp. First player is supposed to win. But the interesting thing is, games are meant to be played, not just sat around in a vacuum. And if you ask a playing question, like, so what concretely should the first player actually do if we're starting with a rectangular bar? What should the first player do? Humanity has no idea, more or less. Doran Zalberger is I think the reigning champion of knowing what to do. And I think he got up to 3 rows or 2, no, 3 rows. Yeah, analyzing 3 rows. 2 rows, there's another strategy, it's a mirroring thing. So we've got a world expert. Yeah, Joe, yeah.
As
please.
I recall, 4x5, there's only one move that the first player can make, which actually wins.
Oh, yeah. Okay. So there might be a path to victory, but it doesn't even say
Let
it's
me
easy
insert
to
a
win.
comment.
Yeah.
This strategy stealing is often attributed to John Nash in the context of the game of hacks that he did when he was undergrad. And the colleague of Neil Sloan, Ken Thompson, did something with Chomp about the uniqueness. So it's a very good game. Thank you.
Quick question.
Yeah.
I'm confused about one thing about the strategy stealing. What if the winning move for player 2 results in a board that couldn't be chomped in a single bite? So then the player 1 couldn't have done that board on their first turn.
Yeah. So what that might look like is I'll show you, something where it would be, it's always a delight giving a talk to any sort of mathematical audience because you always get questions. Just one example that doesn't quite work. So I'll show you something the strategy wouldn't work out. This type of thing would work. Maybe the first person might choose to go here. It's a thing they could do, maybe. And then maybe the second person, their response, maybe they would say, well, in that case, I choose to go up here or something. And dun, dun, they'll say, if that's why I choose to chop here. In which case, the game state, what it would look like would be a sort of rectangle with this sort of a thing going on here. Another one, another one of these, great. And some of them. The game state would look something like this after 2 bytes, if those were the first 2 bytes. And then the objection is like the first player cannot pretend can't steal this. So the first player, like what could they possibly chomp from the original board to make this? Because it's got this like staircase shape that you have to make it out of at least 2 chomps, probably because of the number of ascents or the number of stairs in the staircase. Which is why I very, very, very carefully, but I didn't emphasize it at all, decided that the first player's move in the argument I gave is going to be this very special move in the extreme bottom corner. And if they decide to nibble the tiniest little corner, then regardless of what the second player does, when we're done, it will look like 1 byte has been taken out of it. If the first player deliberately were to do the tiniest little nibble, then the second one, whatever comes in, the second bite would encompass the entire first bite. So it would actually look like something the first player could realistically do in 1 move. I hope I understood the question, and I hope I was pushing towards an answer. But if in either case, please do chime in. I'll sip tea.
No, you understood the question.
Okay, cool. Great. And thank you for the question. Yeah. This game, I like it. It's cool. It's a cool game. It's a beautiful example that you can tell someone on the airplane when they say, "Oh, what do you do?" And you say, "I do math and stuff." And you can just say, "Here's a little game," and they can play. And you can, if it's a long enough plane ride, and if they're bored enough, you could teach them not only how the game is played mechanically, but you could even get at this idea of it's a good idea to go first. And it's this visceral feeling of not just who goes first, but like why. That's kind of built into, I think, a lot of people, which makes a game so fun to study as an object, because they are inherently, almost definitionally, fun things to do. So games, big fan. This game in particular, it's very cool that we know who should win and we don't know what they should do. Not in general. In some cases, we can figure it out. But in general, the state space gets very big. There's lots of different things the game might look like. And that's maybe what I want to talk about next. But any other questions? Super great time for questions about how is the game played? That's a great question. And there's any other questions about why the first player should win? Because that's a cool fact. All right, cool. I'm gonna continue on with the discussion then of I'm gonna keep going with the games route. So it's all gonna be things that sound like games, and you'll say, "Yep, sounds good to me." Not right now. Let's do it right now. Random. Why random? It's kind of part of my sort of I guess my training. I was at Rutgers. I was under Jeff Kahn, and kind of his shtick is like combinatorics, but random stuff. That's just the big thing. It's a thing you can ask. But even before that, I think I really got into probability because in my undergraduate, I had a really influential undergrad professor that I really liked talking with, and he gave me cool puzzles like this one. I don't know. Can't find it. Little puzzles, like these mechanical puzzles, but they're deeply mathematical. And I'd go to his office and he'd hand me a puzzle and I'd say, "Ooh, what's going on with that?" And I think that's where I got the bug for probability. I don't think I got it in grad school. I think I got it from undergrad. So I just kind of like it. It's cool. And at an accessible, very real level, randomness, we can just really just think of that as counting and then reinterpreting the answer. Certainly that's true for a lot of probability type questions. If the probability questions are all very finite and we want to roll 2 dice and we want to know what's the chance that the one die is bigger than the other, we could just count how many outcomes are there total, how many outcomes do the thing we want, and then it's just counting with, pizzazz, counting with style or whatever. You can certainly do, and one does, probability that isn't counting, but at some level, for us, certainly, it's just counting. So any probability question is really the same as just a counting question, but it sometimes gives you different reasons to ask questions, and it gives you an intuition of how to interpret some of those questions. For instance, and I was a bit surprised to find, and this is the beginning of the talk, that the intersection of good old combinatorial games, tic-tac-toe, chomp, there's a game called Nim, these games that are beloved. Tic-tac-toe is less beloved because it's too small, but still, it's a classic. Those and probability, not so much overlap. There is some things here and there. One thing that people do people who care about games, sometimes they throw in probability, and they might say you have maybe, this is not what we did, but things that have happened. One player tries really hard, which is kind of the premise of a lot of the combinatorial games. You want to imagine both players are trying really hard, because otherwise, somebody won, but everyone made blunders the whole time. That's not really what we want to know. What should the ideal happen? So somebody's trying really hard, and some people have studied, but maybe not everybody. Maybe one person tries real hard, and one player is random. And that would be kind of like a grandmaster playing against a child, and the grandmaster tries really hard, and the child just kind of moves the pieces around, and they know how the pieces work, but they don't really know what they should do, and they're not going to think about it. And in this case, the person trying really hard, should win. You would really think. Like
but if the person, the grandmaster, is playing with his own child, he may well try very hard to let his child win. So
yeah. I had so games. The reason I got into games is obvious. They're fun. I remember I would play backgammon with my dad, and it was cute. I wasn't that little. I was probably 12, old enough to be fully aware of what's happening. And it would get to the point where we'd get to the part of the game where our pieces don't interact anymore, and it's just a race to the end. And my dad, in some situations, he'd be winning by a lot, and he's right about to win, and I'd be like, "Oh, I'm gonna lose. You have to win in 3 rolls, no matter what." And I can't win in 3 of the 5 rolls. It was like obviously lost. And my dad would do a thing where he dies, and like throw him down, to leave a little thing, because he'd keep his hand on top, and he'd say, "Oh, the dice didn't come out. I guess it's your turn." And he was just being cute. Yeah. So you can let somebody win if you want. So you can try, exactly, you can try hard for different things. So people have studied this, and this is a sort of a proxy for skill, sort of. One person who's good, someone who's random, or you can say that they're a little bit random or something. But something that I was surprised isn't a thing is, why not everybody's random? Every move is random, just all of them. That's a thing we could do. So when it's your turn to chomp the chocolate bar, you look at the possible options, you pick one without thinking at all, and with all the options equally likely, you just chomp one. So in chomp, you just out of all the possible locations that you could chomp, you just pick one. Sort of to use a little bit of probability language, you pick one uniformly, whereas all the options are equally likely. You pick it in a way that turns it into a counting question, because that makes sense. We like counting questions. You just pick one uniformly at random. And then when it's the next person's turn, they do the same thing. And then when it's your turn, you do that. This is a model that I am surprised, and the moral of the talk is this thing I'm about to say. This is a model that people have not studied. I wrote a paper on it with Polina. Polina and I wrote a paper. We analyzed Chomp. We also analyzed the game Nim, which is another classic game. Turns out Nim is a lot less interesting, and you can understand that completely with randomness, as it turns out. And we analyzed Chomp. But the point of this talk in an ideal world is that you, people who like games, people who like recurrences, people who might like probability already, you folks, do more of this. It's wide open. Pick a game and then say, yeah, what if everybody moves randomly? Like tic-tac-toe, but random. I don't know the chance that someone wins. There's a chance that the first player wins if everyone moves random. There's a chance that the second player wins if everyone moves random. There's a chance that it's a tie if everyone moves random for tic-tac-toe, where ties are possible. You can ask all the questions, and it breathes life into otherwise completely understood games. And also, I'm going to try to argue, it gives you an inherently interesting thing to look at, that it's a natural question to ask, and that it's in some sense, it's not, the right question, but it's a very good question. If you like a game, you should like what happens if that same game is played randomly at all times. If you like subtraction games, you should ask what happens if we play that subtraction game, but both players move randomly. And you should probably ask all the game questions you like, but now they're probability things. Like
Pat,
you might ask,
did anybody do it for chess? It makes sense for chess to have a random move among all the legal moves. Did anybody try it?
Sure does. Yes, in some sense. So this is I'm going to say this a little bit wrong, and I would love if someone chimed in and corrected me, because I would like to know the more correct sentence. But some of the best chess playing algorithms, these days, they're all machine learning. And I think I'm about to describe the one from Google that's called, I think it's AlphaGo is the name of their chess algorithm. I think the way that it does its learning process is it plays against itself. And at first, it probably starts with a rudimentary understanding of chess that's pretty good. But what it could do, and I think it doesn't quite do this, but it emotionally does. It plays against itself randomly and then says, that didn't work out. I should tweak my understanding of the game. And it simulates random games, but then up to a point. So it says it has like some tactics, and then it looks at a certain depth, and then at some other level it's random. And it's this thing that's like, I think it's related to like alpha beta pruning. It's a whole thing that you could do with chess in particular. And I think understanding a question like, if you don't know how good a chess position is, if you don't know how winning it is, one way to get a score is to estimate from this position, what's the chance that white would win if everyone went randomly. I think that's literally a thing that some algorithms do, and I would love to be corrected if anyone has any other things.
Looks interesting. Thank you.
Joey, do you have a thing to comment? Because unmute yourself, and I'd love to hear it.
No, a very, very simple question, a version of what you're talking about. Suppose you have a queen and a king on a board versus a king, and they play randomly. What is the probability that the queen and king will in fact win the game? My guess, it would probably be close to zero.
I would think so too. Winning in chess is hard. You have to get them into a certain location, and even like, if you were actually just decent at chess, you're a kid who's played chess, and you give them a king and a queen versus my king, it can just be, there's a little thing you have to do. You have to move the guy somewhere. It's a very deliberate process. And if you kind of mess it up, the king just kind of gets loose. Yeah, it would probably take way longer than this 50 move rule. I would suspect the chance of winning in almost any position with those pieces would be near zero. So there's that too. I really would suspect a lot of chess would end in a tie because you wouldn't do any obvious moves. And checkmate is even if it's obvious visually, if you were thinking about it, it's not something you're going to stumble into by accident. They'll accidentally hang their queen and the person will be forced to take it. I'm very sure that's what would happen in this game. It just feels like the most likely way it would end is the person with the queen randomly puts it right next to the other king in a way where the king is forced to take it or randomly takes it. I bet it would end probably by insufficient material even faster than the 50 move rule, I would guess. But you could simulate it. What a question. This is what I want. This is exactly what I want. I just want any game, throw some randomness in, and then instantly we got the conversation. Yeah, Eugene,
you said chances are it would end in a tie. I would say chances are it wouldn't end.
Oh, I would think that I would guess that it ends in insufficient material. I would guess the queen gets eaten, and I would also guess that there is this, in chess in particular, there's a rule that prevents the game from lasting forever. If if there's no pawns have been moved and no pieces have been captured after 50 moves, then it's just called a draw, just to prevent games lasting forever. Although that does sometimes turn a win into a tie, very rarely. But any other? I think I saw someone else about to chime in with anything.
Yeah, I just had a comment. I don't know how it works with Google, but Convecta, which is largest chess base, uses just database lookup to find the best continuation in a position. And they record every tournament at certain level is immediately stored and recorded. So now they have a probably best, well, again, I don't know how Google does it, but I know that chess-based player software, there is no randomness at all. There is huge database of all chess games played in a history.
Yeah. It's definitely the most sophisticated chess engines are certainly a combination of many ideas. And without a doubt, the fact that a computer can remember every opening that has ever happened in the history of time is a very strong advantage all by itself. Yeah, exactly. Yeah. So that's huge. These databases are big.
Yeah, what is most important part of their success is that they have very, very fast search in a database of position. Extremely fast with special encoding, and this is like already 35-year-old. They started 35 years ago. The money was given by, at that time, champion Anatoly Karpov. So, and I lost my PhD student to this project.
Anyway, that's not random. So the point is randomness.
Yeah, that's a good point. So, let me talk just for a bit so that way we can get all on the same page of how to kind of conceptualize. And this is a general framework for any random game. And then I'll tell you exactly the sort of stuff we did in the Chomp thing. I'll certainly show you some results. But let's talk Chomp in particular. The exact same thing would happen if you're thinking about chess or tic-tac-toe or whatever it is you want to think about. And it's already kind of some of the language that's been happening is one way to conceptualize the game is we have these positions. And a position in Chomp is going to be a shape of a candy bar and maybe whose turn it is if you care about that, but probably you don't. And then the idea is we have the candy bar starts out looking like this. And then on your turn, you have the option to convert the candy bar into a different shape. And you get to eat based on where you choose to chomp. So you might chomp the very bottom right corner, in which case you'll make it look like this sort of a thing. You might chomp, I don't know, somewhere more exotic. You might make it look like this sort of a thing if you chomped in the rightmost column. You got lots of little options of what you might make it look like. And it just depends on what you felt like chomping. One of the options in Chomp, it's a legal move, which is not advisable, but it is a legal move, is you could decide to chomp the entire bar and there's nothing left. Could do it. Could eat the whole thing. It's always an option. You could, at any moment, just chomp the whole thing. You don't want to do this. It would be a bad idea. You would instantly lose. And, whoa, that was weird. Kind of no matter your skill level, it's pretty intuitive. Don't do the one thing that makes you instantly lose. But in this model, where we're going to play randomly, if we decide we're going to randomly pick one of these moves, come to think of it, one of the moves involves instantly losing. That's weird. Not a thing we would ever do, but maybe. And then from here, it branches into more possibilities. From each of these positions kind of branches into yet more possible things, except for the one where you lose because you've lost. And you get this whole, it's called a game-directed graph. It's a whole thing. Some of these positions actually show up in maybe more than once, so you might feel like drawing those in the same location to keep everything easy. This is exactly like what a chess engine would do if it were looking for tactics. It thinks about you and all possible responses, and then all possible responses, and it does that up to a certain depth, because that makes sense. But not for us. We're just gonna, at each stage, random. And what that looks like is, in this game graph, you'd make a random walk. You start somewhere, and then to use this kind of probability language, it's as if the game looks like something. There it is as a position, and we're thinking, yep, that's where we are, a state of the universe. And then, out of all the places you might legally move to next, all the next legal positions, you pick one uniformly at random, and you just kind of go somewhere. And maybe we ended up here next. And then, out of all the places we might go next, we just kind of pick one. And now we're down here. So from a randomness point of view, it's not like a deeply mysterious object. It's just you start here, and then you're going to go to one of the next nodes, one of the next options. And then you're at the next spot. You go to one of the next ones. It's a random walk. It has probability language and everything. And for that reason, probabilists don't find this an inherently deeply exciting object unless they also care about games. So probability people don't think this is cool because they don't, like, there's the probability part is not mysterious unless they care about games, which is the point. You have to care about games and ask this question about it in order to, I don't know, care about the question. But it's inherently related to the game itself. The game is this graph of what should you do. And when you play the game, you usually try to pick not randomly, but you pick the best direction so that no matter what they do, you have another good place to keep pushing it. So that way, eventually you push it to a situation where the game ends and we know who won. But randomness, if you have a graph you like, you should ask questions that the graph cares about. Like, what happens if you just kind of walk around? What is the average length of a game? Some games end quickly. Some games end in a while. How fast do they go on average? Just trying to motivate that, and boy, does this show up in any game you could want. When it does, you instantly get recurrence relations. So let's pick a thing like the probability of winning. Probability that the player who is about to go will win. Who is about to move will win. From, and then you give it some sort of board, some position. I'm going to call this board B. And let's give this the name that's just a little bit shorter, P of B. The probability the next player will win if this is the current situation and the player is right about to go. And it's a probability because they're going to randomly move, and depends where they go. But it depends, like, analyzing this probability is not mysterious. We can figure it out like exactly. And we'll get a recurrence relation. And the recurrence relation will exactly be involving this graph of the children of the positions the legal moves you could make. And if you did make those moves, you ask more or less the same question, except that the roles of who's going next has swapped. But other than that, you ask the same exact question of, oh, okay, well, if we move, then what's the chance on these other things? It's recursive. And you get something, for instance, if we want to say, starting with, let's do a 2x2. If we want to know what's the chance that if we play Chomp randomly, starting with the 2x2, what's the chance that the first player wins? And we can figure that out by using the kind of probability language. We're going to analyze where they go. And this is exactly this graph. There's 4 possibilities. And the probability, we'll take an average of these things. 4 possibilities. We might make it look like we nibble from the bottom right, or we nibble the next one, or we nibble so it looks like this, or we eat the whole thing. There's 4 things that we might do based on which of the 4 squares in the bar that we can see. There's 4 squares. We might nibble one of them, and there's options 1, 2, 3, 4. for those 4 different things that the game might be looking like next. In which case, if they nibble the bottom right, suddenly we care, ooh, now the game looks like this. And I'm curious what happens, how does the game finish from here? But we've switched the roles of who is currently first and second. So we want to say, we need to switch the probabilities. The chance that the original player wins would be that the next player loses if they had started from this thing. And then they might start from this other thing as the other possibility. Or maybe they start down here. And the one minus is because we've switched which player is currently going first. And if this ever happens, you think about this for a second. There's some base case here. This would be bad. Going here is bad. It should not contribute to the player's thing. There's some whatchamacallit, a base case. If the game's over, then the person who's about to move would win because the previous player just lost. Is just deciding if it's an N position or a P position. That's it. So you have game stuff like the moves are exactly encoded in this recurrence, and so are exactly encoded in the recurrence the win conditions. It has it all. It has the game, which is, what more could you want? And then to get from here, you do the same thing. You recursively split up each of these pieces, and you keep splitting it up. So there's not the recurrence relation for who should win when is not at all mysterious. It's exactly you average the children, and you also have to do a 1 minus because the roles of first and second player have just switched, which is a thing you do when you switch from an N position to a P position. That's exactly what's going on there. So let me just switch to more a little tiny bit more story mode. So my colleague and I we were trying to analyze this for in general, Chomp. Why not every single board? Get a magic formula. Let's go for it. Ambition. But also, it might be hard. So what we definitely did, because of course we did this, and you would too, we wrote up just a program that it takes this recurrence, so it has to give it a little board, which you have to encode as some sort of data structure. And then you have to say, if this is my board, what are the legal moves? There's as many legal moves as there are pieces in the chocolate bar. So that's at least easy to conceptualize. And then you say, okay, now I've got this recurrence thing, and it's just literally a recurrence. You probably remember previous states, make a little database, otherwise it'll blow up. But you do a thing, you program a thing, and you can plug in any shape you want, and pretty reasonably quickly you can get what's going on, especially if you're doing the trouble of making a big database as you go. So we did that, and we did that with who should win, and we also did that with how long does the game take. And one of those questions, we just got a lot of data, because that's what you do. We asked a new question, we don't know what's going on, get a lot of data. And some of the things we noticed, I'm gonna, for the expected amount of time, expected length of the game, which is definitely a thing that probability people would care about. It has a natural combinatorial interpretation. How long does it take? The expected length, we have a great formula for it. It's exactly, I'll show it to you. Let's get a board. Let's do, just so I don't write forever, let's do this one. Let's do this one. How long does it take this board until the game is over on average? And what you do is you index it like a matrix, but you want to start in the top left in case you didn't already do that. And then you multiply these things and take a reciprocal. So it's a multiplication table is what I'm about to write, but I'm going to divide because it turns out that's what you want to do. You write a little multiplication table, and then the expected time is exactly, you just add up all those pieces, add up all the numbers that I just wrote down. It's half plus a quarter. And it's really interesting that each piece adds an amount of time to the game in a very predictable way. If I were to add a piece here, the number that would be there is 1/4. And it adds, on average, a quarter of a turn to the duration of the game, which is kind of pretty. And we discovered that very experimentally by looking at a lot of boards. And then Paulina made a very beautiful, very well laid out thing that she noticed these patterns were arising. And she said, it looks like if I'd add a new square, no matter what the board looked like, if I add that new square, it always adds a quarter. That was cool. And then once we had a conjecture that this is actually what's going on, you can prove it in a few different ways. So that was kind of cool. We know how long the game should take. That's kind of fun. Another probability question you might ask is, okay, well, who should win? And then something really interesting happened there. The probability that the first player wins, randomly so. And that's a great question. We know that the first player should win if they were trying really hard. So you would think that they should win more than half the time because they actually have an advantage in this game. It is advantageous to go first. But very wildly, we noticed out of all the boards we saw, it looks like, and this is, I'll emphasize, a conjecture that we don't know, but it really looks like, even though the first person has an advantage deterministically, you don't want to go first in random chomp, is what we noticed. And that's wild. And we conjecture that that's true, that randomly, it's not good to go first. And I have a heuristic why. The heuristic is, if you're playing random chomp, the situation feels more like you got all these moves. And at any single time, no matter what happens, there's always a chance that you shoot yourself in the foot and eat the entire bar because you randomly ate the entire bar. That would be a bad idea. But it's always an option. And it emotionally feels like random chomp is a little bit like Russian roulette, where it is a disadvantage to go first because the whole game is just waiting until someone goofs up big, is kind of what it feels like, although it's not quite. So we noticed this pattern.
What if you forbid this stupid move?
Love it. Love it. You know what my response is? I would love to read a paper about it, Dr. Z. Okay. It's beautiful. Give that to a student. Boom.
You try to experiment with the variation?
We didn't even look at it, no. But that's an extremely natural thing. Like in chess, you're not allowed to do a move that would cause you to lose. So that's very natural. And it suddenly matters what are the legal moves. Last thing I'll say in my 20 seconds is lots of pretty stuff showed up. We studied it for 2 rows. We know what happens for 2 rows, and we got a recurrence through experimenting. We don't know if there's more than 2 rows. We do not know the answer. If you want to do 3-row to chomp randomly, we don't know the answer, and that sounds great. You should do it. I'd love to read about it. For 2 rows, weird stuff happened. And very recently, we had an email this morning. I'll just kind of show you this last thing. No, I'm done. Thanks for the time. It was nice. Like seeing you. Thanks again.
And we have plenty of time for questions to Pat.
I won't continue talking, but I will show a thing. And please, questions. Yeah, please. Any of them.
So
we got this. Just this morning, we got an email from David Broadhurst, who I think was on the call. I don't know if still is. It was.
I'm here, but I'm a bit tired because I was up all night proving the theorem you're about to show.
Yeah, and I got this. It's the best kind of email you get, where the email said something like, "I read your paper. I had a thought about it. Here's a cool thing." You know, it's the sort of thing you hope. And he had there's maybe I'll contextualize with just pointing at a thing that I don't want you to read at all. We have a formula for 2-row chomp, who should win. And the formula is a little bit, it's this necessarily mouthful of a sentence. There's a formula for it, but it involves some numbers that show up. And it's a weird formula for 2-row chomp, who should win. You can read it. If you Google random chomp, it's the only paper that shows up. But like, here's if it's n things in the first row and then 4 in the second. Anyway, it's a thing. And there's some numbers that show up. We in the paper do not understand what these numbers really are. But then, David stayed up and then wrote this beautiful thing that analyzes these numbers to an extremely high precision to understand exactly how big these new sequences I didn't put the sequences in OAIS. I'm sorry. But he analyzed these things to really high precision, not only getting the leading terms, but also the next terms is up until some very good decay. So that's I just got that this morning. You can ask him or Dr. Z, or ideally you can read about it in some upcoming paper, maybe from David. Would be great. Happy for any of that. Sorry, I just wanted to plug some cool stuff that happened. Yeah. Anyway, yeah. Any questions or comments or anything? Happy.
Well, yes, I've got the following comment, which I made to you by email, that the mathematical structure of your recurrence relation, which is written down there, is very, very rich. It's a sort of thing which a mathematician couldn't have invented by pure thought. It's come from actually fitting lots and lots of data that came to you experimentally. And you know, I'm a physicist. That happens to me. Quantum field theory tells me what problems to solve. I don't have to invent them for myself.
Yeah. And that's a beautiful point that I think is a meta point. In chemistry, they say that nature is the best chemist by far, in that humans can sit in a lab and try to do stuff, but like the best medicines we have for a lot of stuff are things we found in the dirt of an Italian castle, stuff like that, that nature is cleverer and richer than we are trying to be inventive. Or there's the Ramanujan quote where Ramanujan sent all these things to Hardy, and then Hardy wrote back saying, even though there were no proofs, he wrote back saying, all of these must be true, because if they weren't, no one would have the imagination to invent them. And not at all to liken anything that I've done to anything that Ramanujan has done, but to say asking random questions about games is a natural thing, and studying natural questions, pretty stuff should show up. And David understands these recurrences better than anybody on the planet at the moment. And apparently there's some good stuff over there. There's some really pretty things that have happened. And I would recommend you too think about games and just throw randomness in there. It's not really probability. It's just a recurrence relation. You can do it. And I think it's going to pan out.
Anyway, I want to make a comment. That's really amazing. Combinatorial game theory existed for so long, and randomness. So as far as you know, that's the first attempt to combine randomness with combinatorial game theory.
Yes, and it doesn't feel right. So you can read this paper where we wrote about it. The only thing, there were a couple I mentioned kind of earlier. Some games are one player, but not everybody acts randomly. And then Joseph Beck at Rutgers wrote a book about something that is related, but is not about games. It was about graphs, but he wasn't thinking about games. But yeah, it's really weird that it feels weird that people have it, because the probability people, a lot of them don't care about games. A lot of the games people don't care about probability. But I'm just trying to pitch. Come on in, the water's fine.
Lots of games, like card games and backgammon, are by definition games of chance. But famously, combinatorial games was also called games of no chance. So in some
games
sense,
of no chance, exactly. Yeah.
In some sense, you defy them. So it's really nice.
Yeah, I think that I believe that there's a lot to be said about analyzing a game from a random point of view. And I would not at all be surprised if there are deep, meaningful connections, like the Sprague-Grundy values of a game are maybe related to the chance that a player would win if they went randomly. I wouldn't at all be surprised if there's deep, meaningful connections that bridge thinking hard about a game and not at all thinking about the game. They might be more related than you might otherwise think. But nobody knows until you, whoever you are, do the thing.
So I have another quick question. So you have an explicit formula for the expectation for the duration of the game of Chomp. Simply is the sum of the reciprocals of the distances from the corner, right?
Yes.
So,
yep.
Can you say anything about the variance of the random variable duration?
Nope. That's great. Or absolutely. And if a person doesn't like the word variance because they don't like probability words too much, let me convince you that it's meaningful. It's just a QT analog of the recurrence relation. Shove in a T somewhere for something, and then you recover every probability question you want as in this more general generating function thing. If you take, where's the defining recurrence? Take the defining recurrence and then shove an indeterminate variable in there and ask yourself what that polynomial is. And where the heck did it go? This one. Take this thing and just shove a T somewhere. And boom. That's, you get all the, if you can analyze that, you will answer all the probability questions. Yeah. Yeah, Joe.
Yeah, I would like to leave with one number. For example, what is the probability of the first person winning in a 2x4 game? Chomp.
Okay, give me a sec. I started doing this recently, and I think it's a lot of fun. I've got this bulletin board in my office, and then in one corner of the bulletin board, I've started putting a piece of paper from every research thing that I do. That way I can look back and then remember, ideally, like the key moment. And here's the piece of paper that I was scribbling on when I guessed the ansatz that I should have. And somewhere on this piece of paper, there must be questions. So what was it? A 2x2? Did you want that
2
one?
by 4.
Square?
Let's say 2x4.
To 2 rows, 4 columns. So it is 8 divided by 4 times 5 times 6. Plus a half.
Okay, so that's actually
whatever that is.
So it's less than a half. It's more than a half.
They all are. They look like, or whatever I said, should make it the one that's less than a half. Looks like they all are, which we know is true if it has 2 rows. We don't know Chomp with more than 2 rows, but I would conjecture all of them are less than a half. It's a disadvantage to go first.
But I suspect that what Darwin said before, if you remove the possibility of shooting yourself in the foot, as you said, that it will shift to be more than a half.
I would guess so.
But I'm not going to do it.
Yeah, I would. Yeah, I would think so. Or it would at least become much more. Yeah, I don't know. It feels like something. Yeah. It's a lot harder to get any heuristic of what it should be.
Yeah.
You commented at the beginning about random nim. What results are known for that?
So in this paper is called Combinatorial Games Played Randomly, Chomp and Nim. Nim is always a 50-50 coin flip unless it's determined because there's 1 coin in each pile. That's a little bit boring. Nim, yeah, it as it turns out, I was surprised, but it was the first thing I thought of because Nim's a classic. And then when I thought of it, I was like falling asleep while I thought of it. And as soon as I thought of the recurrence and I started calculating a few things, my version of counting sheep was solving this recurrence for certain little positions in my head. Yeah, I got a half, and then I got a half, and then I got a half. And I was like, looks like Nim I did 1 pile Nim first. And I was like, oh, that bizarrely, it's a 50-50 thing. And then from there, because Nim sums are nice, probabilities are nice, you get a half for all of them. It was a little surprising. So Nim is boring. Also, Nim, 1 pile Nim, is 1 row Chomp. And we know 1 row Chomp because we know 2 row Chomp. So you can get it from the Chomp results too.
There's a variant of Nim more interesting called width-off game. Did you try to do it randomly?
You could try to do it randomly.
Okay.
But also, yes, I could. A person could. And I'm very sure it'll be something. They're cool. Yeah, everything I've seen so far, asking about games and random, it has rewarded us for asking that question. Sometimes it feels contrived, but in these cases, it doesn't. It's kind of, there's good stuff inside there already. We don't have to look for it. So if there's a game you like, whatever it is, just throw randomness in the name and then see what happens. Would recommend. Speaking of random, I've got a statistics exam that I need to administer about now. And at some point, the students will get antsy if I don't give them their exam. So I need to leave. But
okay, it's a good time to leave.
Thank you again, everyone, for showing up. I'm
great
very grateful to see all the faces again. Thanks again for the invitation.
Thanks.
See you around.
Thanks, everybody. Thank you.